Okay, well, hello and welcome, everyone. If you're looking for the UCCS speaker series, you're in the right place. This is the final session of the fall quarter component of our series this year. Next quarter, we're hosting a special 6-part symposium on the future of artificial intelligence in California. And today's talk addresses almost a perfect nexus of this and our remaining two themes: adapting to climate change and developing technical solutions to important and often complex policy problems. We've covered wildfire earlier this year, first with Anna Sarah-Lobet, who focused on the aftermath of fires and ways to reduce risk of flooding and mudslides, and more recently with former Insurance Commissioner Dave Jones and Dr. Mike Peterson, who discussed challenges in the California insurance market related to fire and floods. Today, we're pleased to welcome Professor Neil Driscoll to talk about how an advanced camera network can reduce damage from wildfires as our climate continues to get hotter and drier. Dr. Driscoll is professor of geology and geophysics at UC San Diego's Scripps Institution of Oceanography. His research focuses on using the sediment record to understand the processes that shape the Earth, but he's also co-director of UCSD's Center for Public Preparedness and the Alert California Network. As you'll hear in somewhat greater technical detail, this network consists of a vast array of cameras and some very smart computers that make sense of the data. Professor Driscoll received his PhD from Columbia University and is the recipient of many awards, including the Young Investigator Award from the Office of Naval Research, the Heesen and Stork Awards for Excellence in Research, and the Distinguished Crosby Lectureship at MIT. So I'm very pleased to welcome Professor Driscoll to our virtual podium. Neil?
Thank you, Dr. Kravitz. It's a pleasure to be here virtually. So today I'm going to talk to you about Alert California. And really, the whole goal of this program is to prepare, respond, and recover. So here, the mission statement of what we're trying to accomplish is better quantify the fuel loads, better assess the health of the fuels, the moisture content in the fuels, and the soils. So these are things we can do before events. During events, we have over 1,060 sensors deployed up and down the state. These provide early confirmation of ignition, and they provide situational awareness during events where evacuation routes are safe. So after events, we want to understand the impact of these burn scours on sediment erosion and dispersal, biohabitats, and revegetation. So this program has 3 legs to the stool. We want to quantify before. We want to have information and data-driven decisions during, and after events, we want to see how we recover. This is a huge project. This is a picture from Silver Peak in the Inyo White Mountains, looking back to the west over the Sierra. And all of these people play a critical role: computer engineers, network engineers, computer specialists, programmers. We have just a very talented group of people that are really the stars of this project, and I just get to travel around and present it. We've developed a village. All of these entities work with us and collaborate with us: PG&E, SDG&E, Edison. But our biggest partner is CAL FIRE. And recently, we've embarked on a great experiment of having CAL FIRE, their subject matter experts, training our AI when it thinks it sees ignition. How fortunate are we to be in that position? Okay, another important partner in this public-private partnership is Digital Path, who's been instrumental in developing the AI, and I'll talk about that later. So we're in a time of extreme climate. We're having just incredible events, like here in Derna in Libya. Just a few months ago, they got their whole ration of rainfall in a few days. It wasn't it wasn't helpful that the factions there are fighting and infrastructure has been allowed to deteriorate. And so here, during this flood event, 11,000 plus fatalities. This is what extreme climate is doing. It's weather whiplash. It's causing us to have record amounts, the biggest, the worst, the longest the strongest. Look at the temperatures. When you look at the temperature for 2023 summer, it's way above the mean. And we're just looking at, we're heating up the earth. We're heating up the atmosphere and oceans. And as Roger Revelle said, we are conducting the world's largest experiment with CO2. And I would just add to that, the big problem is we're in the experiment. When you look at NASA and you look at the distribution of areas that are above the global average, you'll notice the poles are warming faster. Ice is going away quicker, impacting the polar vortex. Here, Arctic amplification. And our predictions with La Nina and El Nino are breaking down. We're not seeing some of the drivers. So here, we're watching storms either grow very fast or not grow at all, like Otis. Otis was predicted to be a tropical storm. Otis overnight went from a tropical storm in less than 12 hours to a Cat 5 hurricane and just wreaked devastation in Mexico. Okay. And so here, the models didn't predict this because the models are based on previous observations, and we're changing them so quickly. PM 2.5 concentrations. Look at this through time. Okay, here, 2020, the amount of PM 2.5, look at the density. California had air quality like Beijing. PM 2.5 has been correlated with the longevity of life. This is a cascading disaster of these fires. Here's the El Nino pattern prediction. But remember, La Nina predicted dry and colder weather. I think California got anything but. We had 58 inches here at Palomar Mountain. The ski areas in Sierra had record snowfall, snowpack, caused a lot of concern during the melting period and flooding in Lake Tuare. So let's just step back and look at the largest fires in California history. We go back to the Rush, Cedar, the Thomas. All of these fires were 270 plus thousand acres. And they were the largest fires at their time. And then we followed that with the LNU Lightning Complex, the Creek, the Mendocino Complex, and then the Dixie in August. These are million-acre fires. So this is something that we've seen in the last 2 years abate, but it's cyclic. And the following year, if it's dry conditions and we go back into drought, we'll be right back where we were a few years ago. So here, I'd like to just, from Kristen Allison, a 25-year veteran firefighter, 15 years ago, a 100,000-acre fire would be the largest fire of your career. Now we have 1 million-acre fires. It's hard even for us to comprehend. Another cascading disaster of these fires, a good rule of thumb is 100,000-acre fire liberates the same amount of CO2 as 7 million cars operating continuously for a year. Let me just say that again, because this is a good metric to have when you think about fires. 100,000-acre fire liberates the same amount of CO2 as 7 million automobiles running continuously for a year. Here, the cost is in millions, billions of dollars. If you look over here on the right, and you can see the cost to suppress fires shows the cyclic nature of these fires. We don't just build year after year, but you look here, we're in billions of dollars. This isn't for buying engines or supporting CAL FIRE. This is just to suppress the fire. We need to divert some of these funds and invest them before and with forest management. And the firefighters know this. I'm not telling them anything they don't know. So they're getting worse. Can scientists help? Can we use data to drive decisions? And I would say yes. So here, this is the plan we've adopted. On the left is severity of the fuels to fire, susceptibility, fire threat. and you go from red high to yellow less. Over here on the right is a 3-phase program that we've initiated here at the University of California, San Diego, as part of Alert California. The salmon color is already all collected. We collected the largest LiDAR data set ever in one period. Okay, so here we've also mapped huge areas in Northern California. We need to map the orange, which is the coastal range, the transverse range, and the peninsula range. So this is what we've accomplished. So here we've leveraged federal funds at almost 50 cents on the dollar. All the blue is done, and it's quality 1, which means it's at least 8 hits per square meter. We paid a lot of attention to this, and we're averaging 14 to 16 hits per square meter. So we get the resolution of the data at the scale the processes are operating. The salmon color is being performed and flown as we speak, and the green will be flown next year. Okay, so here we're trying to map the health of the fuels, the water content, and quantify are the fuels in the canopy or on the forest floor. We've also collected multispectral data. So the purple is phase 1, and we've acquired 13,000 square miles. Okay, we still have about 45 to 50,000 square miles to map. And so we have a large lift in front of us, but we're continuing to go down this path so that we have information prior to events. We can use data to drive decisions. So LiDAR, what is LiDAR? LiDAR is light detection and ranging. And imagine it's just like using a flashlight, and you could time when you had a pulse leave the flashlight and return. That would be the first return. Usually it's from the canopy or the top of a house. Here is a bridge on Highway 1, and you can see the resolution of the LiDAR. So the LiDAR bounces off the first component, like the tree canopy, and gives first returns, and then it bounces off the earth. And this allows us to strip off the biomass and look at the digital elevation models. We collected this in fixed wing. Here we were hitting pulses of greater than 8 pulses per square meter. Survey altitude was a little higher than usual because in the Sierra, the updrafts and downdrafts are enormous. And here the survey speed was in the order of about 100 knots. So these are what the data look like. This is Mount Whitney right here in the background, and you can see the vegetation and tree types and density. We can go in now and take the first return and look at the second return off the earth, and we can make a bare earth model. And why is this important? This is important because fire goes where water flows. So these canyons, like over here on the right, are chutes where fires can rip up faster and pull in air. Venturi effect, really start to have the fire flare up. So these are corridors where fire can move quickly. So these bare earth models, these digital models, are really important for understanding fire behavior. And also in our case, for understanding what cameras can see unobstructed views of ignition. So we want to know where are the ridge lines, where are the mountains, how are the cameras positioned so they can allow us to triangulate. So this bare earth model is very important. This is looking at Mount Whitney. I showed the previous one was looking to the west. This is looking to the east. Most people don't look at this scenery in detail, but there's Mount Whitney where my cursor is. And you can see all these valleys where fire can flow, like the Creek Fire, where they had to use the National Guard to evacuate people trapped in that fire. The fire exploits the topography and creates its own weather. This is Palisades Sierra. Look, you can see down to the branch scale. Right? We're able to quantify the fuels. We're able to look at the health of the fuels. This is important information into fire behavior and for management. Again, I can make a digital elevation model. And as a geologist, I go, wow, look at these giant alluvial fans that have coalesced to form a bajada. But these data, they serve many purposes, but we're using these data to help understand fire behavior and where the fire is going to go. We can also use the multispectral for forest analytics. Here you can go in and you can identify individual tree types and biodiversity. And this is one of the starting points of looking at the health, species, and the fuel load. And then we get to here. So pairing the LiDAR and imagery is a force multiplier and allows for more accurate and detailed analysis of vegetation. So what I'm showing you here in the top panel is I'm showing you 2015 to 2018 from the LiDAR, imaging the canopy and the fuels. Please use the road to reference yourself from picture to picture. Here in the second row, I'm showing you the normalized difference vegetation index. So blue, purple are healthy forests. And when we get to red, it's unhealthy. So this was the progression through successive droughts back in 2015 to 2018. And we can start to look at the health of the fuels and their ability to combust, ignition. So it's really important that the data, it helps us understand how drought has affected vegetative health. We're also developing approaches. How often do we go out and map the fuels? Is every month or is it just after events? So we're trying to understand the cadence of surveys so that we don't alias the data and we provide robust information to go into the models. So as I said, biomass and carbon estimation. So here, between LiDAR metrics and allometry of the tree species, we can look at the biomass, the carbon content. We can estimate the biomass in the canopy and on the forest floor. It also helps us with wildfire modeling and how we can go in and use these models to predict where the fire will be in 2 hours or in 4 hours. And then our camera networks can provide confirmation or rejection of the model behavior. Finally, we can look at landslide analysis. So this is a multi-hazard project platform. And here you're looking here at the Oso fire in 2014, okay, up in Washington. So here is the area that's going to fail. Please note where my cursor is. So here, increased rainfall over a long period of time, this whole margin failed, okay? And the debris flow went much farther, went across the river, went much farther than models predicted. So the red shows where a sediment is evacuated. The blue shows where it's deposited. Look at the river. It's just chocker block full of sediment. And this is what happened up in the Klamath, and I'll talk about that in a second. So here, the fact the run out of this failure was so large, 429 people lost their lives in this slide. And here you look on the left here, the building, people thought they were safe because the run out from this failure here, which it failed before, they didn't believe would go this far. Well, look over here. Here's the river for reference. It just buried these houses and buildings and leveled them. So a fact that most people don't know is landslides occur in all 50 states. Even flat Florida has landslides. And here, the amount of cost and loss of life is higher than most people expect. The Montecito slide, 23 people were entombed in that slide overnight. These slides are deadly. We need to know more about the runout, how we can prevent and de-water the debris flows so that we cause them to slow down. So here, the mosquito fire, large fire that burned through Placer and El Dorado counties. And here it was the largest fire in 2022. And what I'm showing over here is data from UC Berkeley, where they had treated a small amount of forest management in this yellow area. And where it was treated with prescribed burns, they saw that the mortality rate, the die-off of trees during the mosquito fire was less than in the dense areas. Okay, so here's a pyrocumulus cloud of that fire caught by our cameras. And here's Montecito firefighters monitoring the progress and trying to get break lines established with the mosquito fire at Volcanoville. Here, Robert York, he's a forest ecologist. He believes he's using prescribed burns to mitigate the temperature of the fires. Hot fires are bad, cold fires are good. So I'm just going to read one sentence from his release. It's very clear that fire behavior changed, and the treatments did accomplish that function of reducing fire severity. It's things like this that we need to do, but we need to go in and quantify the forest before the prescribed burn and then afterwards. And then we have data. So if a fire does occur in that region, we can quantify how it impacted mortality of trees. We need to quantify these. It can't just be descriptive. Here's the McKinney fire. All right, the McKinney fire left a huge burn scour, an enhanced erosion and sediment delivery to the Klamath River. It went anoxic and had a huge fish die off. All right, so here's another example of these cascading disasters into our riparian environments, into our reservoirs. Just as I was mentioning, here's the Camp Creek fire before and after, or the Camp Creek before and after the Caldor fire. You can see the color of the water, the carcinogens, the soot. This is really harming our riparian environments and our water reservoirs. These fires are incredible. And with wind events, the Caldor and Dixie fire were the first fires to burn from one side of the Sierra to the other. Why is this important? Well, the crest of the Sierra is not a high fire threat region in anybody's maps, CPUC or CAL FIRE, because it's granitic. It's a granitic dome, but the winds were strong enough to blow embers across these rock domes in the Sierra. We're in a different environment. We're in an extreme environment. The severity of fires is getting higher. So here, this plot, high severity in yellow, total areas burnt in gray. And you can see that the Sierra Nevada, these fires like the Creek, the Caldor that I just mentioned, the Dixie, these fires have incredible severity regions within them. And the biohabitats are not evolved to these type of fires. They're evolved towards the colder fires, the smaller fires. So here, what is Alert California? I show this picture. I'm on the bottom. Falco Kuser, co-PI is on top, and everybody jokes that the condor is better looking than us. So we can go in and we can look at thousands of cameras, but we get watchstander fatigue. How do we use these data, these returns from the wild country, to better confirm ignition, provide the dispatcher information to scale their response? So just recently, we were awarded the best inventions of 2023 by Time Magazine. This is this partnership I mentioned between CAL FIRE and Alert California. We have the greatest fire agency in the world, subject matter experts, looking at our AI and teaching it. What better position could we be in than having a university and an agency that are the best in the world working together to solve these problems? And when I say UC, I mean the whole UC network. So here, this is the position of the cameras we have in California. And on the right here, you can see that this was last moved in a minute. So the top four are the cameras that were recently moved. You can see fire here, smoke in these cameras. We can also go and just look at the cameras that are active. These are all the agencies that work with us that have the ability to move the cameras and look at the AI. So here we've done the AI and rolled it out into CAL FIRE, into their 22 ECCs, into their 2 Intel offices. We've just met with the Forest Service. We're going to roll this program out, this platform, to the Forest Service and provide training and onboarding. It's an exciting time. We also look at recovery. So we have drones with LiDAR and multispectral, and we go and look and map after. So we can go here and just to show you, this is fixed wing data. This is Black Mountain down in San Diego. And this is one of the power line towers. And here's the cables. What I'm going to show you is the resolution our drone can get. So look at that difference. Look at that tower. We're able to image the earth at the scale processes are shaping it. And the reason we can get such great data is the drone can stop and collect hundreds of points per square meter. A fixed wing aircraft cannot stop. So they optimize the amount of coverage, but they're only getting 8 to like 14 hits per square meter. But it provides us a really incredible baseline and a nested approach of using both fixed wing and drone. So this is here, Montecito, and we're looking at some of the slides and some of the long-term vegetation that didn't burn in the recent fire. These data are LiDAR data. We collected over 2.5 billion data points, 200 to 300 points per square meter with the imagery draped over it. This is what we need to collect everywhere. It has applications to many things: soil erosion, landslides. It has direct applications for recovery of people and search. But we're using this approach to quantify the vegetation and examine how slide areas recover, how they disseminate and disperse sediment into our riparian environments, and how do they revegetate. These are data, billions of points of data. This is not a photograph. Okay, so here, I just think that this is amazing that we have this kind of coverage, this kind of capability to go in after events and quantify them. This is the Cane Peak slide in Kern. We were concerned that this slide was going to evolve like the Montecito. You can see the headwall scarps and the detail that can be afforded really quickly. 1 square kilometer of data of this resolution takes a day. This here is Paradise Craggy Lookout. My guys were not happy when they realized the end of the road was here, and they had to carry this stuff up to the lookout. What are we doing up here in Paradise Craggy? Well, we're looking at the Klamath River. They're removing these dams from the Klamath River, and we're working with the restoration, the River Renewal Klamath organization, to document how the riparian environment evolves after these dams are removed. This is an exciting time, and trying to understand the morphologic consequences of dam removal, as well as the effectiveness of putting in the fish ladders and making sure the gradients are such that the salmon can return to the upper headwaters of the Klamath. So this is what the view looks like from Paradise Craggy. We're out in the middle of nowhere. Okay, so here we're in the middle of nowhere. We're able to backhaul these data back to our command center, to our ECC, to do processing, to confirm ignition, to look at other hazards. So here we're using, this is a Starlink receiver. We've done a lot of programming and working with Starlink so that we can backhaul our data through the satellites. Now our window of operation is everywhere. We provide our own solar panels, our own electronics and batteries. We don't penetrate the ground. This is a temporary or long-term station, but it's completely off the grid. We provide everything. So now we can map those most outback areas of the Sierra and the coastal ranges to make sure that we understand ignition. This here is Ball Mountain and Sequoia. Again, we're like 30 miles away from any other station. These other stations shown in blue, but we can backhaul the data through Starlink. Okay, so here, this is one of my favorites. This is Jordan Peak. This was recently installed. So we're installing cameras in these remote areas by using new technology. So we were also on the front page of the New York Times and the LA Times on the same day. And I don't know if they talk to each other or just serendipity, but I don't know too many people that got the front page of both LA and New York Times. But the New York Times went on a little digression with their story. And the reporter thought the main story was, can AI detect wildfires faster than humans? I'm not going to answer that question right now. I'm going to talk to it a little bit more, and then we'll see where we sit. So here, how does our AI work? The camera spins 360 degrees, and it does it every 2 minutes. Takes 6 frames per rotation. AI checks for possible smoke. We display AI in the ops interface, and the ops team verifies and confirms the location, and then alerts are sent out to firefighters, dispatchers, all AI trained in operating environment. So here, the AI picks up the smoke, and you say, well, Neil, I didn't need a AI to look at that smoke. Well, when you're looking at the smoke and it's here like this smudge, and you're looking at thousands of cameras, it's very difficult in the ECC. So what it does is it translates to faster discovery, faster response, smaller fires, potential to save lives and property, less resource downdraw, less response, recovery costs. So here we've fed the machine learning, the AI, with 240 million images of smoke, 70,000 camera rotations. And of these that become alerts is only 0.001% of the images. So we're not overwhelming the firehouse with false positives. That's what's important. We're reducing the noise, not increasing it. We've also built data walls, collaboration with CAL FIRE. This is in Intel up in Sacramento. This here is 5 panel by 3. But what's more important is that this high vision wall can have up to like 20 inputs of different data streams. So the people in the ECC or in the Intel offices can look at weather conditions. They can look at drought. They can look at the health of the forest. They can look at the wind. They can capture all of the parameters that go into trying to understand ignition and how it's going to behave. We've also developed a wall down in Riverside at South Ops. This is Chief Slumpf, who actually caught a fire up in the Cleveland National Forest way before anybody called in 911, and it saved a small fire from turning into a big fire. So here, Phil Selig, the staff chief on this collaboration with CAL FIRE, says the success of this project is the fires you never hear about. And here, that CAL FIRE is the first and only firefighting agency in the world to have such a system in place. Okay, so here we're out in front. California, we're leaders. We're being asked by other states, other countries to help them develop a system like Alert California. So here on the left is Falco Kuster looking at thousands of camera images. You can't do this without watchstander fatigue. The AI helps. It says this camera detected what could be potentially ignition, smoke, or it says something has changed in this picture from the last spin and rotation of the camera. Check it out. My email box exploded over here on the picture on the right. After the New York Times published this image, I got hundreds of emails from all my colleagues throughout my career. And they said, you know, Neil, we really appreciate the New York Times much more because they know your better side. So here, let's look at Owen Fire in Los Angeles. So you're going to see that the AI picks up the smoke right away. It gives us situational awareness, though. The smoke is bent over. It's not dark. So the dispatcher has so much more context and information that they can gauge their response. They can scale it up or down. Okay, so the system is bringing the platform together. It's being used up and down the state. It's solving the problem of interoperability. People don't have to be trained on the system when they're moved from San Diego to Northern California. They've used the system before. Our system also works really well at night. And this here, nighttime detection is very hard because of all the lights and they flicker. But watch here, you can see that blaze. Okay, so immediately you can see the flare up, and nighttime, confirmation is huge. A lot of people at nighttime or in rural areas don't see the ignition. Another aspect of the AI is it takes the digital elevation model that I spoke to you before. We get dialed in of where there's ignition, and all of these cameras have unobstructed view of where the AI thinks it sees ignition. So firefighter could be from another house and never worked these cameras. They don't have to know where they are. They can just go and click on these cameras and see what the camera sees. Quickly verify, like here, that these 3 cameras give us delineate the point. And here you can see the fire, and then you can see it in context of the panorama, right? So we're able to triangulate, we're able to confirm, we're able to see in a regional context, and then we can come over here and we can look at the event log. And the event log shows us that this is a prescribed burn. So it is a fire. We told the AI, yes, you succeeded, this is a fire, but it's not one we have to respond to. We can keep our eye on this and watch how it evolves and hope it's not an overachiever. Okay, so here, then the alerts are pushed out. Over here, you can tell the AI when you're on watch, when you want an alert, and what kind of alert do you want? Do you want a phone call? Do you want a text? Do you want an email? So here, a lot of people like getting a phone call. They don't answer the phone call. They go right away and they look at the alert. And so here's how you can see it work. The AI says, I think this is ignition. It's confirmed that it's ignition. And all of a sudden there's a push, either by phone, email, text. And this is what you see. You get to see the AI, you get to see the ignition, you get to see the Irwin, and you get to see here lat long best guess estimates by triangulation or a long track. So all of a sudden you have all the information at your fingertips very quickly to respond and scale your response. The dispatcher has all of this information readily at their use. So here's the Takuya fire time lapse. So here you're going to see the fire here, and you can see the fire's bent over and then goes dark. So we're gaining a lot of situational awareness from this fire. It's not just early detection, it's having the long-term context that helps the dispatcher scale their response. In the Trotter fire in Kern County, we saw 2 fires. Okay, so 2 fires were detected. And here's the Trotter fire in Kern and burning here. And you're going to see suppression being airdropped. Okay, fire retardant. And so here you see the fire. And this was picked up in very early stages in the AI. And then the cameras provide the situational awareness. There's the drop. And we're getting to the point where we're able to say, with the data we have, should we let this burn a little more? We could use this as a prescribed burn. So we're at the point where the data coming in real time is actually helping drive decisions. This is just the fire model for the Trotter fire by Technosilver that would have occurred without suppression. Because of early detection, we kept the fire to 52 acres. Now, people question and say, well, is this, driving us away? We're suppressing these small burns that could be helpful. Well, we want to use the data to drive whether we let these burns go or not. Structures, it's a complicated problem. It requires more research. So here, it detected 2 fires in the Trotter fire in Kern County. No firefighter or civilian was injured. Structures that were saved were 451, and estimates of value saved is about $218 million by having this early confirmation and detection. Here, I'm just showing you a few fires that happened in Kern County. No 911 call was ever received for this incident. Okay, so not that we're beating them. There's not even a 911 call being to the station, to the dispatch. Again, The cameras helped validate that this was a fire. It was at night, and it took at the location at 9:45 p.m. But before that, it was equivocal. Again, the system works well at night. Here, another incident where no 911 call was ever received. This is the success. If you never hear about the fire, it means that it was suppressed. Our firefighters are safe and they're back in the house. Okay. Early detection is a good tool. Again, another incident here, the Bell incident. So we're just seeing that with these incidents and with the AI and with quick confirmation, we're able to get on, suppress, and be safe. So here, as I read Phil Selig's quote, and we've all just are aligned with this, the success of this project is the fires you never hear about. So here, beating 911 hundreds of times, changing fire response, dozens of fires with no 911. So I'm back to the question that I posed to you. Is AI detecting wildfires faster? We're holding off on answering this question until we get into January or February, the shoulders of fire season or higher fire season. It's fire season last year round now. And we're going to release the data in January, February timeframe, where we have enough data that we actually capture this question and it's robust and we don't alias the signal. So here we're really excited at the preliminary results, but we want to have a really robust data set that we can show how this AI is working. So to summarize, this program is providing early confirmation. It's quantifying fuel loads, providing input to and constraints on fire behavior, defining forest health, guiding forest management. We're in the science world, we want data to drive decisions. And I think we're on the cusp with some of the new aircraft, some of the new AI, potential satellites, all working together to try to solve this problem. It's bigger than any one of us. Thank you.
Fantastic. Thank you so much, Dr. Driscoll, for that fantastic talk today. And I'm going to go ahead and give Brooke a moment to go ahead and turn off the recording.